Hello, welcome back. This is Chapter 9, Section 4, where we're introducing the idea of transforming quadratic functions, which, like I said in the first video, transforming functions, all functions, is a big major theme of Algebra 2. So this is our first real taste with it. Actually, that's not even true. When you guys were drawing different linear functions by changing the slope and the y-intercept, you were transforming functions. It's just that it wasn't as obvious then, so your book didn't bring it up. Hopefully I brought it up. In this section, we're going to introduce vertical translations. What does that mean? And we're going to describe transformations of the parent function. Okay, so we're going to compare the new function with the y equals x squared, okay, or f of x equals x squared right here. All right, so for this example, we're going to be talking about vertical translations. Basically, it goes like this. All right. If I have a function that says x squared plus c, all right, this is going to be this f of x equals x squared, what we call translated vertically. A translation, you probably learned this in middle school, we call that a slide. So we're going to slide the whole graph. Since we're sliding it vertically, vertical means to go up and down, so we're going to slide it up or down. Okay, this will be easier once I switch over to Desmos. If the number that you're adding to the graph, so x squared plus a positive number, if that number is positive, greater than 0, then that whole graph is going to get pushed upwards. And that's true for any function, not just quadratics. It may not always be a c, but don't worry about that. If that number that you're going to add is negative, and adding a negative looks like subtraction. One of the things that I have tried to remind my students is that in algebra, subtraction doesn't really exist. Subtraction means adding the opposite. So if you have something that looks like subtraction, like subtracting 5, you're actually adding negative 5. So if that number is less than 0 negative, it goes down. So again, let me show you using my wife's iPad. So I have the parent function right here, and I'll show you these. These are going to be the examples I'm going to give you. All right. Let's see what goes on there. Stop that. Okay. Now, this right now is y equals x squared plus c, and I'm letting c equals 0. I start out with c equals 0. So this is, again, the original parent function. What happens if I let c be a positive number? So now I'm going to slide this up here, and the graph moves up. You can do the same thing. Just type y equals x squared plus c. It'll say, do you want to add a slider? Say, click sure or yes, whatever comes up. And then you can grab this and move it back and forth. So if I go back down, kind of like where it was at, 0, if I can get to it, we'll pretend. Again, as c goes up, this graph, as c increases, this graph moves up, and you can see it moving up. If I go back to 0, which I'll see if I can get close to, there, hey, I got it. There's a video proof that I was able to get it. What happens if c is now going to be negative? So if I move it the other direction, the graph moves down. I know my hand's kind of in the way. I'll try to do it this way. I'll go around my iPad. That's what happens when you're right-handed, guys. So notice that the graph is going down. Right now I'm at c equals negative 7.4. So if I wrote that as just the equation, it would be y equals x to the second power plus negative 7.4. And that's the same as y equals x squared subtract 7.4. Please remember, adding a negative is the same as subtraction. Excuse me, adding the opposite is the same as subtraction. Okay, because if you subtract a negative, then that's adding a positive. I gotta make sure that I'm clear. These are the things that haunt me. Okay, so what I have to do now is look at the number that's being added or subtracted. Now here's the examples we're going to do, and I'm going to come back in Desmos to show you. But since I've got them here, let's just look. I know that each of them I'm doing something with the x squared. We're going to talk about that. You already know about that. If it's negative, it flips it to a frowny face, and the number that you multiply by makes it wide or narrow. Okay, so we'll get to that. But just look at the plus 2. That means that that graph is going to, from the parent function, is going to move up 2. Vertical translation, a slide upwards this way, up 2. This one's going to go down 3. This one's going to go down 4, and this one's going to go up 9. All right, so I'm going to come back to that in a second. Let's pull out some problems. These are the same problems I was just talking about. We're going to compare each function with the graph of the parent function. And what we do is we start, remember the order of operations, which is PERMDAS? That means we're going to multiply before we add. So if I start at the x squared, first I talk about what's multiplying, and then I talk about what's being added or subtracted. Okay? And if it's negative, I got to break that into two parts. So first of all, the 1/3, all right? This is going to be more narrow. Should write the word more narrow than y equals x squared. Whoop, sorry, I forgot which one I was doing. We'll say wider. I forgot which one I was doing. I don't know why I did that. This one's going to be wider than y equals x squared. All right? So it's going to take my graph and it's going to spread it out that way. The negative, I'll tell you why I messed up. In Algebra 2, we're going to do this, okay? We're going to call this a vertical compression by 1/3. The negative means that I'm going to flip it upside down. But again, just like narrow, wider, that's a bad way of saying it. Flipping upside down, that's a bad way of saying it. We call it a vertical reflection because it's a reflection. It's like a mirror. And then the +2, that's going to have a vertical going up and down translation, which is the fancy word for slide, up 2. Okay, so let's see if that's actually what happens here. All right, so I'm going to change this one to the parent function. Go to 0. So there's my parent function. Let's look at this graph right here. So I've got two things. What if I delete the 2 for just a moment? All right? I'll put it back in, I promise. I'm just hiding it. So you saw that it's wider. Okay? That's called a vertical compression. What's actually happening is that it's actually being squeezed this way. But I know it looks like it's being pulled wider. And again, I don't like that they call it narrow and wide. I'll mention that probably more times than I need to, but we'll just let it go for now. The negative flipped it from a smiley face to a frowny face. All right, now let's put the +2 back in there. +2 now moved it up. So there's three things. It's flipped, it's wider, and it got moved up. I know it's kind of hard to see because you're like, well, where did it move up from? It moved up from where the vertex, which is now 0, 2, was originally down here where the other vertex was 0, 1. Okay, let's hide that one and then we'll do the next one. I'm looking at this one, g of x equals 2x squared. It's not negative, so there's only two things. Okay, it's more narrow than y equals x squared. The actual vocabulary on that is that it is a vertical stretch by 2. There's no negatives, so I only got two things. The next thing is the subtract 3. That is a vertical translation down 3. So again, I'll pull the iPad over. Here's what that one looks like. And you can tell, even though they kind of intersect here, you can kind of tell that the red graph is skinnier, more narrow than the blue graph. That's what the 2 did. And the -3, actually, let's, like I did last time, let's delete that for just a moment. You can tell that the red graph is more narrow. And when I put the -3 in, here's the vertex for the red graph now. If I put the -3 in, subtract 3 in, the vertex moved down to 0, -3. Actually, every point in the entire graph moved down. That's what we call a vertical translation. All right, come back to that in a second. The next problem, get this clean up my workspace here. So the first thing is this negative. This is -1 times x squared subtract 4. So the negative only takes care of the reflection, right? So I have a vertical reflection, and that vertical reflection goes from a smiley face to a frowny face, so it's going to be upside down. And actually the mirror is over the x-axis. But of course all that is stuff that we'll cover in Algebra 2. You're multiplying by 1, which doesn't change, so this is the same width as x squared, just the only thing is that it got flipped upside down. The subtract 4 here is a vertical translation down 4. So let's take a look at this one, and I'll even start off with it like this. So here's negative x squared, here's my positive x squared. So boom, and I'm sorry, I don't want it to be the same color. Let's go green, okay? So this blue graph flipped down to the green graph. And when I subtract 4 now it moved it down 4. All right, let's look at one more. This 3, g of x equals 3x squared plus 1, it's positive, so there's no reflection. It's going to still be a smiley face. This is going to be more narrow than y equals x squared, where this one was the same and this one was wider. I don't like saying it that way. So what it would be better if we say that it is a vertical stretch. That's way more descriptive, by 3. The plus 9 tells me that I have a vertical translation up 9. So let's take a look at that last one. Had to move so I could see it. So it's kind of hard to see that it looks more narrow. So let me get rid of the plus 9 for just a moment. Now you can see that the green graph is skinnier than the blue graph. Okay, that means that it's actually a vertical stretch, but that's really hard to see with quadratics, and that's one of the things when we get to Algebra 2 that we kind of have to play around with, like graphs that are not quadratic so people can see it. So I understand if it's a little confusing. For now, probably that's why Dr. Berger just wants to talk about narrow and wide. What happens if I do the plus 9? So look where the green graph is now. Watch it. If I do plus 9, it moved up 9. So the original vertex was at 0, 0. Now it's at 0, 9. And there's more of the graph if you want to see it. Okay. We'll see you in the next video.